the title of the talk reads as Cosmic Inflation Driven by the Barrow Holographic Dark Energy. Okay, so you can see that basically, okay, there are two parts of this talk. Okay, the first part deals with the cosmic inflation and the mechanism, okay, related to it. And second part deals with the Barrow holographic dark energy. And in the third part, actually, I'll talk about what we have actually done in the paper. Okay, so I'll move on to my next slide. Okay, so cosmic inflation. Okay, what is this actually? Okay, this is actually an event which occurred, okay, just after the Big Bang. And this and during that the event, what happened is that, okay, the universe actually went through uh, a high rate of expansion. Okay, the expansion maybe the expansion of the scale of the exponential expansion. Okay, so it is the explosive upscaling of the young universe. Okay, that is what I've written over there. Okay, so the rapid expansion, okay, just after the Big Bang, okay, that is what we call as the cosmic inflation. Acha. Okay, the next part is that uh, the, the event was actually very short-lived. You can see over that. From 10 to the power of minus 36 seconds, okay, to 10 to the power of minus 33 seconds after Big Bang. Okay, so the so it lasted for a very short time, isn't it? Okay, then we have uh, basically we have the two main uh, events, okay, which actually forms the basic two pillars of the present cosmological model, okay, which is the early time inflation that you can see over here. Okay, this is the Big Bang. Okay, just after it we have the cosmological inflation, and after the subsequent steps, okay, we reach the final modern universe, okay, the present universe, okay, that we see today. Okay, these two parts, okay, the early time inflation and the late time cosmological uh, ac- acceleration, okay, they actually form the two basic pillars of the cosmological model, okay, as we know of. I think the slides are running very slow. This can actually be. I'm going to switch off my cam. Okay, my machine is running very slow. Okay, so we come to the next slide. The slide says that we come to the theory of a theory of cosmological inflation. You can see uh, that if we want to build a theory of cosmic inflation, okay, we actually have to develop some extra degrees of freedom beyond the standard general relativity. Okay, the standard theory of general GR, we have to build on some extra degrees of freedom over there. Okay, uh, to, to incorporate, okay, that high rate of expansion over there. Okay, but the thing is that the detailed particle physics mechanism is not known till date actually. So what do? We actually have some speculations with us. Basically, there are two speculations. The first one reads as the dark energy. Okay, so what is the dark energy? Okay, they are basically the exotic fluids with high negative pressure, okay, that can drive that acceleration, okay, the huge rate of acceleration. And the second part is the modified gravity, which has the source from the gravity, okay, uh, that is of the gravitational source, okay. So so here we are actually dealing with this first part, okay, the dark energy part, okay. Okay, now the most suitable models of this dark energy, okay, that can actually uh, explain this cosmic inflation is basically the scalar field models, okay. These scalar field models are basically built on basically two things. Okay, they have the field and they do have a potential, okay, by which we can actually explain those scalar field models, and they can very effectively actually uh, 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 describe the cosmological inflation. Okay, the theory was actually developed by uh, uh, three people, okay, that I have over here. Okay, Starobinsky, Guth, and Linde. The 2002 Dirac Prize and 2014 Kavli Prize was actually given to this theory of inflation. Now, why do we need this theory, and why do we uh, 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 actually, what do we actually get from this theory? Okay, the theory, the theory is basically used to explain a few things. Okay, the first thing is that, okay, the theory of cosmic inflation do explain the large-scale structure formation of the universe. Okay, the uh, small quantum jitters, okay, that we have during the early times, okay, they get magnified, okay, during this cosmic inflation, and they form the roots, okay, roots for the structure formation of the universe. Okay, means all these galaxies, the planets and the stars that we see, okay, they can be properly explained, okay, by this theory. Okay, without this theory, okay, we do have a gap over here, okay, and we cannot explain this properly. Okay, then we can explain the flatness and the isotropic universe, okay, by this theory. Okay, and finally the what do I say, the evenness of the CMB fluctuations. Okay, we see an even CMB fluctuations. Okay, they can be very well actually uh, addressed, okay, by the theory of cosmic inflation. Okay, we come to the holographic principle. Okay, now what is this? Okay, this is actually a principle which states that the entropy of a system is characterized by its area and not by its volume. Okay, now this seems to be a bit of a surprising or radical theory, okay, where we generally tend to believe, okay, that all the information of the system must be stored in the volume, isn't it? But this theory actually says that all those information of those of of all the objects, okay, which have fallen into the black hole must be encoded on the surface of the event horizon. We do not need the volume actually. You can see over here in the picture, okay, that we have this 2D universe over here, okay, the 2D uh, projection of the universe. Okay, now if we get all the information on this surface, from these informations, okay, we can actually build up the whole 3D universe over here, okay, which is actually called the hologram. And this principle is called the holographic principle. Okay, so what does it basically mean? It basically means that if we have a volume, okay, all the data of that volume, okay, can be encoded on a surface surrounding it. Okay, this is how, okay, means if we suppose have a volume, okay, and all the informations of the volume can be actually stored in this surface. Okay, this is what the holographic principle says. Okay, and the concept actually comes from the black hole thermodynamics and string theory, and it can be a very, very good alternative explanation for the dark energy. Okay, so we come to holographic dark energy. Uh, okay, the formulation of this theory is based on the holographic principle. Okay, just what we have seen seen in the previous slide. Okay, so um, just a minute. Yeah. Okay. So the formulation is based on the holographic principle. Okay. So what we basically have over here is that we do have an entropy law. okay, which is actually where the entropy is connected to the area. Okay, so the entropy, the standard Bekenstein entropy is based on this formula over here, where the entropy is given by area by 4. Okay, where we have considered the Newton's gravitation constant as 1. Okay, uh, basically it should be a by 4g, and we have taken g as 1 over here. Okay, and the area is basically 4 pi l square, where the L is the IR cutoff. Okay, and the IR cutoff is basically the largest distance, okay, that is admissible to the theory. Okay, just a minute. uh, yeah. Okay, so this is the largest distance, okay, that is ad- admissible to the theory. Okay, that is why we need this IR cutoff, because we are actually residing in the quantum regime, and so we should have a largest distance. Okay, largest distance that the theory can admit of. Okay, so this IR cutoff actually uh, separates, okay, the quantum regime from the classical regime over here. Okay, okay, the density of the standard holographic dark energy may be given by this. Okay, where you can see that the density rho is inversely proportional to the square of the IR cutoff over here. And c is a parameter, and this mp is the Planck mass. Okay, so this whole portion is a constant, and rho is actually uh, proportional to uh, the the cutoff to the power of -2. Okay. Now, if we do have some corrections or modifications, okay, to this law of entropy, okay, which will actually come from the quantum gravity framework itself, that can lead that uh, uh, that can lead to some modified form of holographic dark energy. Okay, I mean, these are the standard. Okay, these are the standard holographic dark energy. Okay, that I've discussed over here. All these parameters. Now, if we do have a correction to this form of entropy, okay, we will get actually some modified holographic dark energy. Okay, we have some examples over here, like the Salis entropy, where we modify uh, the area law by this formula. Okay, you can see the difference from here, that if we put delta as 1 and gamma as 1 by 4, we will get back, okay, this standard Bekenstein entropy. Okay, and from this we do get the uh, the holographic dark energy. Okay, similarly, we have the Renai entropy. From here, we can get the Renai holographic dark energy, and then the Sharma metal. Okay, we also have the Kaniadakis holographic dark energy. Okay, so there are various possibilities. Okay, all these modifications actually come in from the quantum gravity framework, and we can have the different forms of these holographic dark energies by modifying the general framework over here. Okay. Okay, so we come to the Barrow entropy, okay, which is the main portion of the paper that we have written actually. Okay, you can see that the model was proposed by Professor John D. Barrow. Okay, and the most striking feature of the model is that the model is inspired from the shape of the COVID-19 virus. Okay, which we are very very familiar nowadays. Okay, uh, uh, past 2 years we have been living with this pandemic. Okay, and we have uh, seen this structure. Okay, seen this structure many many times. Okay, now what is this actually? Okay, see, we have the quantum gravitational effects, and from those effects we actually get the complex fractal features in the structure of a black hole. And now now okay, how does it look like? Okay, let's take an analog. Okay, we have a Koch snowflake over here. And you can see the diagram over here. Okay, we have a triangle. Okay, now if we break apart the middle one third part. Okay, suppose we take out the middle one third part of each side. Okay, from each side we take out the middle one third and build a triangle over there. And then again, we continue the same thing, okay? For each triangle, we take out the middle 1/3, okay, and build a triangle there. Okay, so if we continue likewise, okay, with more and more steps and the iterations, okay, we will get a complex feature like this. You can see over here, okay, more and more number of steps of the same thing. Okay, we will get a complex feature like this, which we call as fractal basically. Okay, so this is the Koch snowflake, which was actually developed in a 1904 paper by Helgi von Koch. Now if you take the spherical form of this, okay, the spherical analog of this Koch snowflake, okay, that will look like something like this, you know, something like this, okay, which is similar to the COVID-19 virus. Okay, we have a sphere over here, okay, then some more spheres gets attached to it, and then again some more spheres do get attached to that also again, okay, and it goes on and on. Okay, to demonstrate this, I would like to play a video for you. Just a minute. Please have a look at this video. Okay, we have a sphere. We get more and more spheres attached to it. More and more again. More and more again. Okay, so this is what is analogical with this COVID-19 virus over here. Okay, I'll play the video once more. Okay, so we have a sphere. We have more spheres to it. Then again and again, okay, more and more spheres come in. Okay, this is how we do get the structure of the COVID-19 virus. Okay, Barrow was uh, uh, highly inspired by this structure, and using this structure, he actually proceeded to form a different type of holographic dark energy. Actually, he actually uh, proposed the Barrow entropy. Okay, Barrow proposed the Barrow entropy after getting inspired from this shape of the COVID-19 virus, you can see. Just a minute. Okay, so we come to the Barrow entropy law. Okay, you can see that the complicated structure actually brings in more and more area to it. You can see that more and more spheres gets attached, and the area becomes more and more, isn't it? So this actually modifies the black hole entropy, and we have this modified entropy law, where where a is the area of the horizon, and this is the Planck area, and delta is the main parameter over here, which is the Barrow parameter, or uh, the Barrow parameter over here, and which is actually responsible for all the deformation which is induced by the quantum gravity. Okay, so all the quantum gravity uh, effects come in from this delta. Okay, so near the scale where the quantum gravity effects dominate, okay, the surface area of the black hole, okay, may not be given by the normal 4 pi rg square, where rg is the Schwarzschild radius. Okay, we can have more to it due to the complex fractal features. We will have more area to it. Okay, so a 2D surface will behave like a, a 3D feature, okay, 3D surface, okay, rather I would say, more and more area will come in, and in the limiting scenario, we will have much more intricacies to it. Okay, just not like a 2D surface, but much more to it, okay, behaving like a 3D surface. Okay, so the 2D surface will actually behave and will house all the information of a 3D volume. Based on this, okay, Barrow holographic dark energy was uh, constructed by Saridakis. Okay, you can see this is the density of the Barrow holographic dark energy, where C is a constant. Okay, this is the C, and with this the IR cutoff over here, the L, and delta is the Barrow parameter. You can see that for delta 0, okay, this actually reduces to the standard holographic dark energy. And if delta tends to 1, we get all the modifications and all the fractal features actually come in. Okay. Now, why do we study this? Okay, we study this because BHDE do have a far richer structure and cosmological behavior, which was shown by Saridakis in his paper. Okay, he actually showed that Barrow holographic dark energy does have a far richer structure and cosmological behavior. Okay, and this is the motivation. Okay, why we study this form of holographic dark energy. Now for the length scale, okay, the IR cutoff, okay, capital L that I'm dealing with, okay, we have various choices, Okay, there can be various choices for L. Okay, first is the future, uh, the event horizon. Then we can have the age of the universe, from where the age graphic dark energy comes in. We do have the inverse square root of the Ricci curvature. We can also have the combination of the Ricci and Gauss-Bonnet invariants. Okay, from these we get the Ricci holographic dark energy and the Ricci Gauss-Bonnet dark energy. We we also have a fifth type, okay, which is the combination of the Hubble function and its gradient, okay, which was given by Granda and Granda Oliveros, okay, which we call the GO cutoff. We can this is how it looks like. Just a minute. Yeah, the Granda Oliveros cutoff. This is how it looks like basically. Okay, we have the Hubble parameter and the time derivative. Okay, so we finally come to our study that we have done. Okay, me along with Shayoni Maiti, okay, who will be a speaker. Okay, maybe tomorrow. Yes, I think tomorrow she'll be speaking on something else. Okay, so the paper was actually computed by Shayoni Maiti. Okay, uh, the study actually deals with the inflationary mechanism driven by this Barrow holographic dark energy, and it is published in JHAP in this volume and issue. Okay, so what is the motivation? Okay, the motivation is basically driven by the fact that, as I've already told you, that Barrow holographic dark energy is successfully used as a candidate for the late cosmic acceleration. Okay, so the question comes in that why not? Okay, why not check the inflationary mechanism using it? Okay, so we were basically motivated, okay, to check its role in driving this early time inflation. Okay, since it is very successful in driving the late cosmic acceleration. Okay, and we know that we can have a mapping between the two forms of inflation in the early time inflation and the late time acceleration. Okay, both are forms of accelerations of the universe. Okay, so what we do is that we consider the flat Friedman universe as we do in the late universe. Okay, this is a very common metric. Okay, that we know. We derive the from here we get the Friedman equations. Okay, the known forms. Okay, rho BHD is basically the density of the Barrow holographic dark energy, and rho m is matter. Okay, we may have actually excluded matter over here because during inflation we know that uh, the dark energy is basically the dominating constituent of the universe, and we may not consider the matter. Okay, but still we have kept it over there. And and in the second equation, okay, PBHD is basically the pressure of the Barrow holographic dark energy, and we have actually uh, kept out the matter pressure. We haven't considered the pressure of matter because uh, that is negligible, okay, for the inflationary scenario. Okay, then we have the very common conservation equation. Okay, we have considered uh, there is no interaction between the constituents of the matter and the dark energy. Okay, there is no interaction you can see over here. and this omega is basically uh, the uh, the equation of state parameter, okay, which we have calculated in this way. You can see that we have all these parameters of the Barrow holographic dark energy. C is coming from the Barrow holographic dark energy. L is the IR cutoff, which have been considered to be the Granda Oliveros cutoff. Okay, this is what I have already shown. Okay, the length cutoff is actually inversely proportional to the Hubble parameter over here, and using this we get this. Okay, this is the IR cutoff given by the geo, uh, the uh, the, the Granda Oliveros IR cutoff. Okay, now considering the E folds, okay, we actually simplify the equations and we reach this form. Okay, this is the form that we reach. Okay, we are actually trying to calculate the Hubble parameters over here. Okay, okay, so what we do is that uh, since we know that during the inflation, okay, the field actually uh, evolves very, very slowly. Okay, we have these slow roll parameters over here, okay, given by the epsilon 1, epsilon 2, and so on, okay, which are actually functions of the Hubble parameters and their the time derivatives itself. You can see that we have a recurring formula over here. Okay, the following parameters, okay, do depend on the preceding parameters. You can see over here. Okay, we have calculated this flow roll parameters for our model, and you can see that over here we have the Barrow parameter, and looking at this form, we should know that delta actually cannot be 2. Okay, so for our model we do have a constraining of the model that delta cannot be equal to 2. Okay, uh, we have all the different parameters over here. You can see that beta is coming here. Beta is coming from the cutoff. Okay, we have C is the parameter coming from the Barrow holographic dark energy, and so on. But the main parameter is basically delta. Okay, delta actually determines the effects from the quantum gravity. Okay, so we have calculated the Hubble parameter values. You can see that at the beginning of the inflation, okay, slow roll parameters are very, very small. And the phase actually ends when the first slow roll parameter becomes 1 actually. Okay, we have calculated the Hubble parameters both at the end of the inflation like this and at the beginning of the inflation. Okay, so Hi is the H initial over here and He is the H end. Okay, this is at the end of the inflation. This is and this shows the Hubble parameter at the beginning of the inflation. Okay, we have we have a, we have also calculated some observables, okay, which are related to this study. Okay, the first one is the tensor to scalar ratio, and also we have the spectral scalar index, scalar spectral index. Now, what do these actually signify? They actually tell you about the nature of the primordial, okay, density perturbations, okay, that were actually present at those early times. Okay, these are uh, the expressions which govern them. Okay, we haven't actually derived them from the perturbation analysis, but we have actually used the approximate values. And these are our expressions, okay, that we have found. Okay, R represents the tensor to scalar ratio, and this NS is the scalar spectral index. You can see that all these expressions actually contain all the parameters of the model. Look at the delta and the C, the alpha and the beta. Okay, all these parameters actually govern these values. And from the Planck data, you can see that we have R. R is the tensor to scalar ratio, which should be much less than 0.11, and the spectral index, okay, must be almost equal to 0.96. Okay. Just a minute.
Prabir,
Yes.
may you compile it in 1 minute.
Okay, I'll try.
Thank you. Time is over.
Okay, I have I basically reached the end of my talk, but my slide has actually got jammed. I don't know what is happening. Okay, so if you want me to stop, okay, then I'll stop. Okay, because maybe I'll be having one or two more slides. Okay, but I don't know what has happened over here. My slides have actually stopped. Okay, so I think I'll stop over here by finally saying that that from this study, okay, what we actually find is that the Barrow holographic dark energy is basically a good model, okay, since it can accommodate, okay, uh, both the early time inflation and the late time cosmic acceleration in its framework. Okay, and probably the model demands, okay, much more study in future, and we can actually find a lot more interesting things out of it. Okay, for some future studies, I would like to say that we can actually go on to study the non-flat nature of this. Okay, studying the model with the non-flat universe and maybe non-isotropic universe as well. We can also go on to do a perturbation analysis. Okay, from where we can get a better the understanding of the scenario, and we can also check our model with the cosmological data and constrain the model. Okay, so I would like to thank the audience for listening to me, and I hope that they found it very interesting.